Have you ever really thought about the invisible architecture that, runs our entire world? I mean, everything, from your morning coffee to streaming a movie at night, it's all powered by this one unseen engine. Today, we're going to pull back that curtain and take a look at the engine itself, databases.
I mean, seriously, how does that even work? How does your bank or an airline or a huge online store handle that absolute storm of information and not lose a single piece of it? How do they keep track of every single account, every flight, every order, and do it all flawlessly?
Well, the answer is this amazing piece of tech, the Database Management System, or DBMS for short. This thing is the real unsung hero of our digital lives. It's the software that brings perfect order to what would otherwise be total chaos, letting us store, change, and pull out information with unbelievable speed and accuracy.
All right, so Section 1, designing the blueprint. Because before a DBMS can do its magic, you need a plan. You can't just throw information at it and hope for the best. You've got to design the blueprint first, to bring some structure to all that information chaos.
And this is, without a doubt, the most crucial first step. You wouldn't build a skyscraper without a super detailed plan, right? Well, it's the same idea here. You don't build a database without first figuring out exactly what kind of data you're going to be storing and how all those different pieces are supposed to relate to each other.
So that plan starts with these fundamental building blocks, which we call entities. Now, don't let the fancy word fool you. An entity is just a thing we want to store info about. It could be a person, like a student, an object, like a book, or even a concept, like a bank account. Basically, they're the nouns of our database.
And if entities are the nouns, then attributes are the adjectives. It's that simple. They're the specific details we care about for each entity. So for our student entity, the attributes would be stuff like their name, their age, their unique ID number. It's these characteristics that really bring the entity to life.
Okay, so you take all of these entities and their attributes, you put them all together, and what you get is the master plan. This is called the schema. Think of it as the complete architectural blueprint for the entire database. It defines every single table, every field, and all the rules or constraints that control how everything connects.
Now, this is a really important idea to wrap your head around. The difference between the plan and the reality. The schema, that's the permanent blueprint. It's like an empty library with all its shelves perfectly labeled and organized. It's stable, it doesn't change. The instance, on the other hand, well, that's the actual collection of books on those shelves right now. It's the live data, and it's changing all the time.
Section 2, speaking the language. Okay, so our blueprint is done, the library shelves are built. Now what? How do we actually start putting books on them, or, find the one we're looking for? In other words, how do we actually talk to the database?
Well, it turns out we use two different languages. Think of DDL, the data definition language, as the architect's toolkit. It uses commands like create and alter to actually build and change the structure, the tables, and the schema itself. Then you've got DML, the data manipulation language. This is the librarian system. It's for managing the books, the data, inside that structure, using commands like select and insert.
And here's that architect at work. This simple line of DDL code is literally an instruction that says, create a new table, call it students, and make sure it has spots for an ID, a name, and an age. And just like that, a new shelf in our library is built and ready to go.
Okay, now the librarian steps up. This DML command is basically us asking a question. We're saying, hey, could you select the name and the age from our students table? And the system goes and fetches exactly that information for us, and nothing else. It's how we get the data we need when we need it.
All right, Section 3, keeping data tidy. So we know how to build the structure and how to talk to it. But over time, with millions and millions of entries, things can get messy. So we need a system for keeping everything tidy to make sure the data stays accurate and efficient.
This is a massive problem in the real world. Imagine if a customer's address is stored in 3 different places, and they're all slightly different. Which one do you send the package to? That's how you get massive confusion and really unhappy customers. So how do you stop your beautiful database from becoming this messy, tangled, repetitive nightmare?
The solution is this process called normalization, and honestly, it's kind of like a professional decluttering service for your data. First, you make every piece of information atomic, which just means you break it down into its smallest possible part. So instead of one field for address, you'd have separate ones for street, city, and zip code. Next, you hunt down and remove all the duplicated data. And finally, you organize everything into small, logical tables that are all linked together. This is absolutely key for keeping the database fast, reliable, and trustworthy.
Okay, final section, databases in your world. Let's zoom all the way back out. We've talked about blueprints and languages and tidying up, but what does it all really mean for you and me? Let's connect this back to that invisible architecture that's powering our modern life.
Every single time you use an ATM, book a flight, buy something online, or check your grades at school, you are directly interacting with a super sophisticated database system. They are the absolute backbone of banking, travel, e-commerce, education, you name it. This stuff isn't just some abstract computer science topic, it is literally woven into the fabric of our society.
When you really stop and think about it, our modern world is built, piece by piece, on top of databases. They're the foundation holding up so much of what we all rely on every single day. Which leaves us with one last and pretty critical question. What happens when that foundation gets challenged? What happens when it fails?